Welcome to a reading from The Lucasian Legacy, the Lucasian Professorship of Mathematics at Cambridge University, 1663 to 1993, by Robert Bruen, as read by his son, Garth Bruen. Paul Dirac, 1932 to 1969. Of course, the most famous geniuses of theoretical physics in the 20th century were Niels Bohr, Albert Einstein, and P.A.M. Dirac. They went far beyond conceiving models or explaining some experimental facts. Einstein revolutionized our concepts of space, time, and gravity. Bohr created the most important concepts necessary for dealing with atomic reality. Dirac succeeded in unifying relativity theory with quantum mechanics, leading both to the concept of antimatter and to quantum field theory, a consistent way of dealing with the interaction of matter with electromagnetic and other fields. Victor Weisskopf. Physical laws should have mathematical beauty. This statement was Dirac's response to the question of his philosophy of physics, posed to him in Moscow in 1955. He wrote on a blackboard that is still preserved today. Paul Adrien Maurice Dirac, 1902 to 1984, known as P.A.M. Dirac, was the 15th Lucasian Professor of Mathematics at Cambridge. He shared the Nobel Prize for Physics in 1933 with Erwin Schrödinger. He is considered to be the founder of quantum mechanics, providing the transition from quantum theory. The Cambridge Philosophical Society awarded him the Hopkins Medal in 1930. He was awarded the Royal Medal by the Royal Society of London in 1939 and the James Scott Prize from the Royal Society of Edinburgh. In 1952, the Max Planck Medal came from the Association of German Physical Societies, as well as the Copley Medal from the Royal Society. The Akademie der Wissenschaften in the German Democratic Republic presented him with the Helmholtz Medal in 1964. In 1969, he received the Oppenheimer Prize from the University of Miami. Lastly, in 1973, he received the Order of Merit. Dirac was well known for his almost antisocial behavior, but was a member of many scientific organizations throughout the world. Naturally, he was a member of the Royal Society, but he was also a member of the Deutsche Akademie der Naturforscher and the Pontifical Academy of Sciences, Vatican. He was a foreign member of Académie des Sciences Morales et Politiques and the Académie des Sciences France, the Accademia delle Scienze Torino, Italy, and the Académie Nationale dei Lincei, Italy, and the National Academy of Science, United States. He was an honorary member of the Fellow of the Indian Academy of Science, the Chinese Physical Society, the Royal Irish Academy, the Royal Society of Edinburgh, the National Institute of Sciences, India, the American Physical Society, the Tata Institute for Fundamental Research in India, the Royal Danish Academy, and the Hungarian Academy of Sciences. He was a corresponding member of the USSR Academy of Sciences. The worldwide respect he earned for his work was well deserved. A prolific writer, Dirac published over 200 works between 1924 and 1987, mainly papers in physics journals on topics relating to quantum mechanics. His book, Principles of Quantum Mechanics, published in 1930, was the first textbook in the discipline and became the standards. Some predictions made by Dirac are still untested because his theoretical work was so far-reaching, but many other predictions have been verified, assuring him of a special place in the history of physics. Dirac was 3 years old when Einstein published his famous papers on relativity in 1905, and a year old when his predecessors, Joseph Larmor, began his tenure as Lucasian professor. Physics had just begun its incredible transformation of the 20th century when Dirac arrived on the scene. Dirac came to Cambridge as a graduate student in 1923 after graduating from the University of Bristol. As a student in mathematics in St. John's College, he took his Ph.D. in 1926 and was elected in 1927 as fellow. His appointment as university lecturer came in 1929. He assumed the Lucasian Professorship following Joseph Larmor in 1932 and retired from it in 1969. 2 years later, he accepted a position at Florida State University, where he lived out his remaining years. While at Cambridge, Dirac did not accept many research students. Those who worked with him generally thought he was a good supervisor, but one who did not spend much time with his students. A student needed to be extremely independent to work for Dirac. One such student was Dennis Sciama, who later became the supervisor of Stephen Hawking, the current holder of the Lucasian chair. Dirac's lectures were attended by Sir James Lighthill while he was a student at Cambridge, and Lighthill was Dirac's successor to the Lucasian chair. Dirac offered the first course in quantum mechanics in Britain, entitled Quantum Theory, Recent Developments. Among his students was J.R. Oppenheimer, who later on was in charge of the Manhattan Project, which created the first atomic bomb. Dirac's work should be understood in the context of the development of quantum physics. His theoretical work had been underway for several years before his entry into the field. It was plagued with difficulties, in part because of the radical change in the way one thought about the world around us, and in part because it was a difficult problem. The important developments of the beginning of this century were carried out by Max Planck, Max Born, Niels Bohr, Albert Einstein, Werner Heisenberg, Erwin Schrödinger, and Wolfgang Pauli. Quantum mechanics was brought to life during the few short years of 1925 through 1927 by most of these men. Dirac was the first to apply quantum mechanics to an electromagnetic field, using the method of second quantization. His work contained the basis for quantum field theory, which Dirac called quantum electrodynamics. The singular delta function was invented by Dirac in order to prove two problems that were equivalent. The delta function is now used in many different areas of mathematics and physics and is considered basic. One of the major breakthroughs was the use of an algebraic version of quantum mechanics based on Poisson brackets. Heisenberg had developed equations that were not working exactly the way he wanted. Dirac realized that he had seen a particular expression of the problem earlier. When he applied the brackets, he overcame the difficulties and gained insight into the problem. He saw that the equation had implications that Heisenberg did not acknowledge, thereby holding back the necessary development of the general theory. The problems now appear somewhat simple, with the hindsight of tremendous development and insight over more than half a century. The problem was that of commutativity and multiplication. It is elementary that two numbers, say 2 and 3, when multiplied equals 6, whether you write 2 times 3 or 3 times 2. The order of multiplication is not relevant, but the order of a matrix multiplication, in fact, does make a difference. One would expect that we could calculate the motion of an object by knowing where it was and how fast it was moving. In the everyday world, this is certainly true, but in the world of the atom, it is not true. The problem is that we are unable to know both the position and momentum of something, which, in this particular case, the something is an electron. In fact, the more certain you are of an electron's position, the less certain you are of its momentum and vice versa. This is a basic statement of Heisenberg's uncertainty principle. There are some important ideas to understand to fully appreciate this rather non-intuitive concept, but the end result was that Dirac found the way to connect classical mechanics with quantum mechanics by this non-commutativity property. In 1927, Dirac united quantum mechanics and relativity by deriving a relativistically invariant form of Schrödinger's wave equation, predicting positively charged electrons, which were seen later in 1932. He also predicted that antimatter will annihilate when in contact with matter. He is best recognized for pulling together all of the disparate theories of quantum mechanics. He was able to justify the spin of the electron on a theoretical level which had eluded physicists up to this point. Spin was considered just another number that needed to be calculated for things to make sense. It was this insight that separated him from others of the time and won him the Nobel Prize in 1933. By 1928, Dirac had produced great steps forward along with other physicists of the time. However, altogether the steps caused confusion, since not all of what was known was consistent and some was contradictory. With characteristic insight, Dirac produced an equation now called the Dirac equation, with 4 parts that describe the motion of an electron. Many things suddenly fell into place, and new equations followed describing electron collisions, interaction of photons and electrons, and the correct formulas for the spectral lines of the hydrogen atom. These equations were not possible until Dirac produced his equation. It was one of those moments when everything that is in confusion suddenly becomes clear. It was so momentous that there was talk of everything being figured out, and there would be nothing for physicists to do. Clearly, that thought was premature. The Dirac equation, as is often the case with a great step forward, produced some questions and new predictions that were unexpected. For example, it was not just a mathematical artifact that second-order equations have 2 roots, one positive and one negative. The reality was that matter was properly represented. The possibility of negative energy appeared, which Dirac initially called holes. He saw a particle the same size as his electron, but with a positive charge instead of a negative one. It was not easy for him to see this, but eventually he did. The antiparticle of the electron, called the positron, was discovered in 1932 in a cosmic ray experiment. The antiproton was found in 1955. Dirac's life was dedicated to physics with no interests outside of this work. But, besides quantum mechanics, he did work on isotope separation, magnetic monopoles, large number hypothesis, and other physics areas. The large number hypothesis was based on Dirac's belief that very large constants should not exist in nature. Somehow these large constants that did exist were a consequence of the age of the universe. One of the interesting implications of his work that predicted the positron was the prediction of a magnetic monopole. It is common knowledge that a magnet has a north and south pole, which opposites attract and sameness repels. The idea that a pole could exist in isolation is quite foreign. Although theory predicts its existence, none has been found. His work in isotope separation was a step from his theoretical world into the world of experimental physics. He had done some work in the 1930s, but stopped when his colleague Peter Kaptiza found himself unable to leave the Soviet Union because Stalin had revoked the necessary exit permit. In the 1940s, the war effort dragged Dirac back into isotope separation. A group at Oxford was looking for an efficient means to do it. Dirac's method worked, but it was not considered the most cost-effective. However, he did continue to contribute to the effort and even wrote a report on the statistical method of isotope separation that contained concepts still used today. Thank you for listening to this segment of The Lucasian Legacy, the Lucasian Professorship of Mathematics at Cambridge University by Robert Bruen. To learn more or support this podcast, go to lucasianchair.org or our Instagram account, Lucasian Legacy.